In this video we're looking at computers and their components. This is 3.1 in CIE 9618, but obviously covers other exam boards as well. So we can look at what a computer system is, and that's a combination of hardware and software. The hardware are the physical parts and components that you can touch, and software are the programs that run on the hardware, they run on the computer. Together, hardware and software we can refer to as a computer system. You need both of those things to actually be able to do anything. We can look at this basic model of a computer to define what a computer actually is. If it can input data, process it, output it, and store data, then it's a computer. Input devices vary. There's lots of kinds of input devices. You've got manual ones, automatic ones, there's basic ones, and more complex ones. So ones you'd be familiar with, things like keyboards, mice, touchscreens, all of these can be used as inputs. A touchscreen is both, it actually is an output and an input. But all input devices provide data to the computer to be processed. So input means into the computer to be processed. Some automatic input devices include barcode scanners, mag stripe readers or magnetic stripe readers that you might find and use on bank cards, optical mark readers that are used often for exam papers, and all kinds of sensors to detect things about the world around us. An output device is one that takes data that's been processed from the computer and then does something with it, for example, display it to the end user. So in our model, input devices take data and put it into the processor, and output devices take that processed data and do something with it. So examples include monitors or display screens, projectors, speakers, headphones, and printers. And there's a few printers that are useful to really know a little bit more about. They're laser printers, inkjet printers, and 3D printers, especially for CIE exam board. And you can watch these videos to find out more about how they work. Another thing computers need to be able to do is store data. It's very difficult to actually do meaningful processing unless you can remember things and store data temporarily. So we need storage devices as well. A storage device just stores data. It could be temporarily, or it could be permanently. There's two kinds that we're interested in here. Primary storage is memory that can be directly accessed by the CPU. The CPU can go immediately to primary storage and get data it needs to process. Whereas secondary storage, you can't directly access it by the CPU. The CPU has to request that it's fetched first if it needs some data, and the fetched data moves into primary storage, and then the CPU can get access to it. So primary storage, directly accessible by the CPU. RAM and ROM are both primary storage. RAM is random access memory, called random because you can get to any part of it. You don't have to sequentially read through it. So it's a bit of a strange name for it. It's not random as such. It just means direct. You can get directly to the locations of memory you need. And that stores currently running programs and data that's in use. The memory is volatile, and volatile means that it needs power continuously in order to remember the data, to keep the data safe and consistent. Once the power is turned on, that memory, that data starts to be lost. ROM is read-only memory. And again, originally read-only memory was read-only, you can only read it, but now again it's a bit of a strange name because there are ROM that you can write to, but we'll come on to look at that later. But ROM is used for startup code and settings, the stuff you need when you first turn the computer back on again after it hasn't had power. So when it first gets power, you need to find somewhere for instructions and data. You can't use RAM because that's lost everything. You need to use something that's non-volatile, and that's usually ROM. Comparing the two, RAM, generally speaking, has a much greater capacity than ROM in at least most general purpose computers, because the RAM needs to store potentially many programs and a lot of data, whereas ROM only needs enough to get the computer started and some settings. There's a couple of types of RAM that we look at. SRAM, which stands for static RAM. This is faster, but it's more expensive. It's used for things like cache. This uses quite a few transistors. It uses about 6 transistors and includes a latch circuit so that it can remember data. And it doesn't need to be refreshed all the time, hence the static. So it will stay for a period of time, and you don't need to keep refreshing it for that to be there. DRAM, or dynamic RAM, is slower than the SRAM, but it's cheaper and it uses less components. So you can fit more in, hence it says more dense storage. So we can store more data in a physical amount of space. We use this for RAM because RAM needs to be bigger, and it doesn't necessarily have to be as fast as things like the cache. It uses a capacitor and a single transistor, which acts as a switch to allow for reading and writing. But the capacitor, because it loses its charge over a very short period of time, needs to be refreshed multiple times a second to keep that data up to date and keep it holding its value. So they're the two different types, and you need to be able to know which ones, how they're made, what sort of basic structure they have, and the advantages and disadvantages of each kind of memory. And then we've got ROM. So like I said, originally ROM was read-only, and the first stages, first iterations of ROM, they were just set during manufacture, used a physical mask to set the values within the chip, and could not be changed then on. If you needed something else, you'd have to get a completely new ROM chip and install it. Then programmable read-only memory. This is ROM that's made as a blank chip, and you can program it once. Okay, so you could buy bulk blank chips and then program them as you want them and install them on your device. But those are written off the board, and then put onto a board and installed. EEPROM is programmable read-only memory, so you can write to it, but you can also erase it. So it's not a once-only writing process. You can erase it and write it again, but you erase the entire thing, all the settings, and then rewrite the whole thing. It's erased with UV light, and this is done off the board as well. So you have to take the chip off the board, wipe it with UV and rewrite it, and then put it back in the board. EEPROM, electronically erasable programmable read-only memory. This can be erased, but not with UV. It's erased electronically. So you just use a bit more power and you can reset the contents of the chip. That can be done on the board. So this is done widely now for all kinds of devices like TVs and printers and so on, so that you can update the contents of ROM whenever you want to. For example, with a firmware update, you could just do that using this method. And you find this sort of memory, this basic type of memory, in things like USB drives, SSDs, and so on. So to recap on differences between ROM, PROM, EEPROM, and EEPROM. So ROM is written by the manufacturer, so it's made and set, that's it. It's written using a physical mask. You can't erase it. You can never rewrite it. It's non-volatile. They're all non-volatile anyway. and typical use would be for something that's mass produced and will never change, so it's set. Prom, the user writes it, but only once, so they program it. That's done by blowing fuses within the ROM. You can't erase it, so it's only written once. It's non-volatile, and you might use this for production, like prototypes, small runs, where you're testing something out and you just want to see if it works. And then later on, you might go to mass production. EEPROM, EEPROM, the user can change it repeatedly, but in order to do so, they need to rewrite. The first writing can be done using electricity, but after that, to wipe it, you need UV light, and the chip's removed from the circuit. The number of rewrites is somewhat limited, and this is sort of legacy embedded development purposes. Finally, the most common, like newest version, EEPROM, the user can repeatedly rewrite or write to it using electrical signals. They can do it whilst it's still on the board in the circuit. It can be rewritten thousands of times, used for things like BIOS, firmware, and flash storage. So we looked at primary storage, RAM and ROM, things that are directly accessible by the CPU. Now we look at secondary storage. Secondary storage is non-volatile. It will keep the data even when the power is off. It's used to hold programs and data permanently. We say permanently, obviously it may not be permanent, you may delete it in the future, but effectively it would hold it permanently. Three main types of technology that we use for secondary storage. These are magnetic, optical, and solid state. Magnetic devices, magnetic storage, all use the magnetic field properties to store data. We can use the polarity of a magnetic field to represent zeros and ones. We have hard disk drives and magnetic tape. Hard disk drives are typically used inside computers or for portable storage, external hard disk drives, and magtape is used for archiving purposes. So looking at hard disk a little bit more, the components you need to know about, the whole thing is sealed in an enclosure because you can't risk getting dust or particles inside the disk. There are platters, one or more platters. These are disks that are rigid disks, and they're coated in a magnetic material, a ferrous material. There's the read-write head that can move around, so it can move according to how the actuator arm moves. And that actuator arm is controlled by a motor. It's called a voice coil actuator motor to allow extremely fine movements, very controlled movements of the read-write head. Data is organized on the disks in tracks, and then they're split up into sectors. In the middle, there's a spindle motor that spins the disk around, and then you have connectors that allow you to connect it to your motherboard on the computer, or to, say, a USB port. So platters are rigid, they're made of aluminium or glass, they're coated with a magnetic material. You can have multiple discs or platters around the spindle to give you extra capacity. The motor spins the whole thing at constant speed. Once it got up to speed, it'll stay running at the speed, say 5,400 or 7,200 revolutions per minute, even faster in enterprise disks. So you divide the surface of each platter into concentric tracks, split that into sectors, and a sector is the smallest addressable unit of storage. The read-write head floats just a few nanometers above the surface of on a cushion of air dragged along by the spinning platter. That's why it's very, very sensitive to having dust and particles in it, and why it's all sealed. It reads by sensing tiny magnetic field changes and writes by flipping the magnetic orientation of a spot on the track. So we can make it north or south effectively to represent 1 or 0. The actuator arm holds the head and sweeps it radially across the platter to reach different tracks, and the motor moves the arm. The sealed enclosure keeps out the dust and moisture, and then we have the connectors. Magnetic tape uses the same basic principle, using magnetic orientation, but this time instead of on a platter and a fixed disc, it stores it on a long thin strip of plastic film coated with a magnetic material. The read-write head magnetizes regions of the tape to represent the bits and can read the patterns back again. The access, though, on magnetic tape is sequential, unlike hard disk drives where we can go to specific locations. With magnetic tape, you have to go through sequentially along the tape as it's read. That means that it takes a long time perhaps to find data that you wrote before. So getting data back from a magnetic tape can be very slow, but writing it to the magnetic tape is quite fast because you're writing it sequentially as the tape goes round. Magnetic tape has very high capacity and low cost per gigabyte. It's a very cheap form of data storage, and it will last for a very long time if kept properly in storage. Also, it's offline and removable. That means that you can put your backups wherever you want in a separate building, which is more secure. Then we've got optical drives. Optical drives use light properties instead of magnetics. And we can store data on a disk by having what's called pits and lands on the disk. These are areas that behave differently when light is shone at the surface of the disk. We've got CDs, DVDs and Blu-rays, which all basically use the same approach, just with varying degrees of data being stored and different frequencies of laser light and so on. But they all basically use the same process. So the disc itself is a plastic disc, effectively with coatings, and within that you will find pits and lands. A lens will focus the laser light onto the surface of the disc, and you have something called beam splitter that allows you to shine light at the disc, and then what comes back, the light that comes back, can be deflected onto a detector. And then you have the laser diode that generates that laser light. So the difference between a pit and a land is that pits and lands reflect light differently. So if light comes back at the particular point as expected to the photo detector, then you can tell what that data is, whether it's a 1 or a 0. So those pits and lands are the patterns of those as the disk spins around and the laser reads different part of the disks. You can detect the sequence of 1s and 0s. So there are different methods of making these disks depending on the particular type of disks. But let's take CD-ROM for example. Now CD-ROM, the disk itself is stamped and has extremely small microscopic pits. These are the depressions, and the land, which is flat areas. And this is arranged in a spiral track on the disk, and it's coated. The disk is coated with a reflective aluminium layer. So the diode fires low-powered beam with different frequencies. Green, I think it was green for CD, red DVDs, blue, violet for Blu-ray. So the shorter the wavelength, the more data you can pack into the same physical area. So the beam splitter lets the outgoing beam pass straight through towards the disk, but when the light comes back, it diverts it sideways towards the sensor. The object lens focuses the beam to a tiny precise spot on the reflective layer of the disk. When the beam hits a land, it can reflect strongly. When it crosses the edge of a pit, it causes a change in the light interference pattern. So we can tell the difference basically as we're moving across the disk. And the photodetector measures those differences, measures the intensity, and determines whether 1 or 0 has been present. Our third technology we use is solid state. And solid state uses electronics rather than magnetics or optics to store data. Store data in memory cells. There are no moving parts at all. When you want to write data, the drive applies a high voltage that forces electrons to tunnel through an insulating layer, and then they settle inside a floating gate transistor. And that process of pushing the electrons through this insulating layer is called quantum tunneling. The layer has to be very thin, you need a fair bit of power to force the electrons through, but once they're through, they will get stuck there and keep that charge. So that keeps the charge because the floating gate is surrounded by the insulator and won't let the electrons pass back out again. So this is a non-volatile approach. That data will stay there, the charge will stay there, and you don't have to keep refreshing it all the time. The presence or absence of charge indicates whether or not we have a 1 or a 0. So when we consider what we want to use for secondary storage, whether we're going to use magnetic, optical, or solid state, we need some criteria to judge this by. And we can use these kind of criteria. What capacity does it have? So for example, how many gigabytes could I store on it? What's the data transfer speed? How fast can I transfer data from the device to my computer or to RAM? How reliable is it? How long does it, on average between failures on these kind of disks? Is it years or months? What is the reliability like? Durability is different to reliability. Durability is how does it cope with harsh conditions. So can it cope with being knocked, dropped, vibration, high temperatures? What kind of things can it cope with? Portability is how easy it is to move around. Is it small physically? Is it light? Does it need a lot of power, or can it be powered by battery? That all comes into portability. And then of course cost, but not the cost, absolute cost, but a cost per gigabyte or other unit of memory. So how much does it cost to actually store that amount of data? Here's a table comparing those kind of criteria for the different types of device we might have. I've just lumped all the optical ones together. So capacity for original CD-ROMs is about 700 megabytes, quite small. Multi-layer Blu-rays, you can have about 100 gigabytes. Optical is slow for data transfer. It's fairly reliable, but you do get drive failures because they're mechanical devices that can wear out and break. Not really durable. They are susceptible to scratches on the surface of the disk. Heat and UV can affect them, and over time they will rot, they will degrade. They are highly portable, they're lightweight, they're cheap. The media themselves, the drives not so much, but the media is very lightweight and cheap. And it's the physical shape of it being flat is good for things like putting in books and magazines. It's pretty cheap for the media, but the drives themselves are becoming a little bit rarer and hard to find. So then hard disk drives, so storage wise, great for capacity. You can have large capacity hard disk drives. which is something like between 1, 22 or more terabytes. Speed is moderate. It's better than optical, about 80 to 250 megabytes a second. Reliability is good, millions of hours for drives, modern drives. Not very good for durability. They are sensitive to shock, vibration, they're sensitive to magnetic fields. A head crash can destroy data. They're not really portable, but there are small hard disk drives, low-powered ones that you can have some devices, but again, not brilliant for portability, especially when you consider the problem with durability when they get moved and dropped and things. Low cost of storage. They are a cheap method of storage, relatively speaking. Then magnetic tape. You can very high capacity magnetic tapes, 6 to 45 or more terabytes on a tape. They're fast if you're transferring sequentially, reading back sequentially or writing sequentially, but obviously not if you want to do direct access to something. So they'll do about 300 to 400 megabytes a second. They're very reliable, about 2 million hours. They're sensitive to heat, humidity, magnetic fields, so they do need to be stored carefully. There are no moving parts on the actual tape itself, so the tape itself is not particularly sensitive to vibration or dropping. They're quite portable. The tapes are portable. They can be shipped, they can be transported from one place to the other, containing lots of data, but don't take up much space or don't weigh very much. Very low cost at scale, so probably the best thing for if you're storing a huge amount of data but don't need to access it that much. And then solid state drives. These have improved an awful lot over the last 10 years or so. We have 250 gigabyte to 8 or more terabytes. Enterprise versions can be up to 100 terabytes or more. They're very fast, so they're the fastest data transfer rates. They last well. They weren't brilliant at the beginning, but they've improved a lot in terms of their reliability. Very robust because there's no moving parts. You can drop them, vibration doesn't affect them, but they can lose data if they've been unpowered for a very long time. They're very portable. They're light, small, light, durable. They don't use much energy because there's no physical parts to move. Although they're a little bit expensive. Again, that's come down an awful lot. They used to be significantly more expensive than hard disk drives, but now it's getting a lot closer. All right, let's have a look at embedded system. An embedded system is just a computer that's inside some other device, a machine or something. Sometimes people get a little bit confused about saying things like it's a computer inside a computer, which obviously is not right. It's a computer inside a device such as a washing machine. They have one specific function. That means they can have a simple architecture compared to, say, a general purpose computer. So they'll be generally small, use less power, but not be flexible. They can only really do one thing. Okay, let's have a look at buffers. When devices are communicating, they may not be able to do so at the same speed. One may be able to produce data faster than the other one can process it. And also there may be a problem with timing. They may not be able to precisely coordinate or synchronize the timing of those operations. So what we can do is we can put a buffer between the two. We have the producer producing data at a variable rate. It may be very bursty. That means that sometimes it's going to be generating data very quickly, and sometimes slowly or not at all. And then we have a consumer at the other side that's actually taking that data, and that may be taking it at a steady rate, processing it as it can. And the buffer acts as an intermediary so that there is always, ideally, a regular supply of data for the consumer to be reading. No matter what the producer is doing, there should be some data in the buffer that the consumer can read from. Now, we can get times when the buffer is completely full, and when the buffer is completely empty, and obviously the aim is to try and avoid that as much as possible so that we can keep a smooth processing flow going. Monitoring and control systems. These are two kinds of systems that we need to look at. A monitoring system is one that just collects data and then it can be used by a human, a person, later. Whereas a control system collects data and uses it to make changes automatically without the need for a human intervention. Now, a controller is a type of computer that can be used to make decisions based on the inputs from the sensors in the control system. The sensors collect all the data, they pass it into the controller can look at that to make decisions. And then something called actuators can be used to make the changes to the actual physical system. There's lots and lots of sensors that you could be using. Here are some of the more common ones. A temperature sensor, or sometimes referred to as a thermistor, could be used, for example, in greenhouse monitoring, a central heating system, or an oven. So it'll just detect changes in temperature, and it does so electronically. A light sensor, light dependent resistor. This will vary resistance based on the amount of light hitting the sensor. Could be used in street lighting or in a house for room lights. A pressure sensor measures weight, so it's effectively a weight or pressure sensor, used in burglar alarms and washing machines. Humidity sensors, how much moisture is in the atmosphere, in the air around, so it could be used in a greenhouse or weather station. Moisture sensors could be used for automatic plant watering systems, so we put a moisture sensor in the soil next to a plant, and then we can tell when it needs to be watered or not. Sound sensors or microphones could be used for noise activated alarms or a voice activated system. Infrared proximity sensors used for things like automatic doors, intruder detections, counting objects, and so on. A pH sensor could be used in a swimming pool or a chemical process. Motion sensors used for security lighting, burglar alarms, and so on. And then to control things, we use actuators. Actuators generally a component that converts energy from one form into another. So it could be from electrical energy into physical movement. Now, electric motors, there's lots of different kinds of motors, but they have a rotating shaft, used in everything from robot joints to fans to disk drive spindles. Solenoids, which is an electromagnet that pulls or pushes a plunger in a straight line, so it can convert into straight line motion. Voice call motors, like the one used in the hard disk drives, this can be used to precisely move objects. Hydraulic and pneumatic actuators using pressurized fluid or air to generate large forces. So commonly used in heavy machinery, construction equipment, and some robotics. And piezoelectric actuators, so they contain crystals that change shape slightly when voltage applied. So this is used where you want precise small movements, for example, camera autofocus. It's often necessary to carry out a conversion between analog and digital signals in these kind of control monitoring systems. especially the control system here, where you need to actually control devices. Your inputs may be analog, and your outputs may be analog, and you need to do conversions along the way. So if a sensor is producing some sort of analog data, then we need to use analog to digital converter before it can be processed by our digital computers or our microcontrollers. And then the output may need to be converted as well. So we have the processor will create a digital output which needs to be converted to analog and then sent or used by the actuator. And feedback's a really important part of control systems. What we have is what's called a feedback loop, and it's a continuous from the moment the system is turned on to the moment it's turned off. There is a continuous feedback loop happening. So what happens is we have input sensors generating data that's processed. The controller checks to see whether that input data is within acceptable limits, if that's a stable, acceptable status or not. If it's not, then it's going to do something to tell the actuators to make a change or multiple changes. And then that will change the system, but then we need to check again to see if that was enough, and if not, do it again. So we keep doing that again and again and again. Obviously, external factors are changing, so the system has to be constantly adapting to the external changes so that the system is working as intended. Okay, that's the end of 3.1. Next is 3.2, which looks at logic gates.